Hello, everyone. Unfortunately, Ryan Grant couldn't join us today due to last-minute complications, so it'll just be me presenting. So I want to continue the PGAS HPC discussion and specifically talk about the SHMEM programming model. And the work I'm presenting today is the SHMEM over LibFabric implementation that works on multiple fabrics through LibFabric, but doesn't sacrifice performance or scalability in doing so. So the talk is going to go as follows. First, I want to just do a brief overview of LibFabric. Then I'm going to talk about SHMEM and introduce SHMEM. Then I'm going to introduce the code base that we've implemented and open source the SHMEM-LIBFABRIC code on. Then I'm going to talk about why the SHMEM-LIBFABRIC implementation is scalable, portable, and performant. So let's start off with some background. First, after all these talks, I'm sure we have some familiarity with LibFabric, but the main aspect I want to tease out of that discussion is really getting back to the unique collaboration we have in this organization of having the labs coming together with the vendors to work on pushing forward the fabric interfaces of today and seeing how we can always improve upon the work we're doing. So historically, what's been happening in the network interface for HPC applications is there's just been an exposure of what the hardware is able to provide, and then the applications are left to write the middleware to overcome any gaps semantically between what the application is trying to do and what the network interface can provide. And so the OFI working group came together to sort of redefine this approach to be more application-centric. And in this way, we can make a tighter semantic match between what the applications are trying to do and what LibFabric is going to, or what the network interface is going to provide. And an instantiation of this ended up being LibFabric. And what's indicative of this good semantic match is the thin transport layer middleware that ends up being implemented to go between the application and the network interface. And so what I really just want to emphasize is at the heart of this is that the app-centric design that LibFabric is going for is going to enable the performance, scalability, and portability we all care about in for our HPC applications. And so the SHMEM-LIBFABRIC implementation is a great embodiment of us achieving this goal because the co-design of SHMEM-LIBFABRIC as well as the LibFabric interface kept LibFabric true to being application-centric. It kept the requirements for what the PGAS community and specifically SHMEM was asking for as was defined by the labs during the OFIWG'S discussions and making sure that was kept as a first-class citizen in the LibFabric development. And what this led to is a very thin middleware layer that connects the SHMEM API semantics to the LibFabric API implementation. And so by being application-centric and having this be embodied in the SHMEM-LIBFABRIC code base is really why SHMEM-LIBFABRIC is able to be performant, scalable, and portable. So I realize it's a diverse crowd of people. Paul did a great job of introducing the PGAS programming model, but just to quickly reiterate, for those who are unfamiliar with SHMEM, it is a HPC communication programming model with a focus on RMA and atomic point-to-point messaging, and it does this in a distributed shared memory model paradigm. It also has your usual suspects in terms of collectives with barrier, broadcast, reduce, and recently all-to-all and strided all-to-all. So the SHMEM, OpenSHMEM-LIBFABRIC implementation has been open sourced, and it's in the Sandia-SHMEM repository, and the GitHub link is right there. So essentially what we did is leverage this existing open source repository that was initially built for the Portals 4 transport implementation and was used by Sandia Labs to experiment with some Portal 4 extensions and its mapping to SHMEM. And so we reused the collective implementation and locking and inserted a LibFabric implementation into the transport layer. Additionally, we found the PMI structure to be a process management structure to be a little bit limiting in the code base, and so we extended that as well to encapsulate its own Hydra PMI instantiation so that when you build the library, all you need is some PMI compliant launcher to get the test suite working with your this SHMEM implementation. So we are closely following the OpenSHMEM standard, and we are producing stable releases that follow it as well. We have the 1.2 compliant release, and we also have the newly minted 1.3 release. This is the most recent OpenSHMEM spec, and we were actually the first to be 1.3 compliant. And what's notable for this release, at least for what I think is notable, is the true non-blocking API that's now in the SHMEM API, and we also now have an all-to-all collective implementation. What's great about this code base is it has minimal dependencies. It's very SHMEM-centric, and we're trying to make it very easy to use because since we're in the open source space, we're very eager for collaboration from all across the OFA space. And it's a great vehicle for making sure, LibFabric keeps true to being app-centric for the SHMEM community, but also to help drive forward the OpenSHMEM specification and make sure that as the community is coming up with new features to add to the spec, that they're salient and they've been tested and in an open source space that people can grab and work with ease. Furthermore, we're very rigorous in terms of our software quality. We open collaboration, but if you're going to try to add some code to the code base, it's going to go through our Travis continuous integration testing framework, which runs the OpenSHMEM test suite, including the Fortran tests, over multiple interfaces and iterates over all the environment and variable options that you can use in the code base, and it also runs on independent environments. And we are also utilizing the GitHub software development process, using the pull requests, doing review, using the issue tracking functionality. We encourage the community, if they have any issues with the portability, to let us know about it, and we'll try to address it in a timely manner. And this is an example of what the Travis testing framework looks like for a pull request. As you can see, we run it over an iteration of a different combination of the options that are available for the code base. So now I want to kind of move the conversation more towards the aspects that we garnered from the OFI working group that were put in place into the code base to enable scalability and performance. So these are some of the features that the community had told us would make for a good performant scalable SHMEM implementation that are now instantiated in LibFabric. And the first of which is the scalable endpoint enumeration. So we've talked about in a lot of these talks, we care about reliability between communication with our endpoints, but we also want them to be connected in a way that can be scalable. And so this gives way to the reliable connectionless endpoints that are in LibFabric. Additionally, with SHMEM, it sees the different processing elements as ranks that are enumerated with integers, and so logical addressing is a great semantic match to this requirement for SHMEM. Additionally, with an RMA paradigm, we need to have some mechanism for understanding when an outstanding communication has been completed, and so an efficient way to do this is with a remote completion mechanism. This is also something that is a completion semantic exposed by LibFabric. Furthermore, it's nice to have a lightweight completion mechanism. A queue is a heavyweight object for just needing to know if something did or did not complete. And so remote counter is used for this purpose. Furthermore, as some talks have talked about, PGAS is really known for being able to do a battery of small messages back to back and then ask for completion on those messages. But for creating a small message itself, we wanted to be able to accelerate that pathway, and this is through the FI inject functionality that's exposed through LibFabric. Additionally, we don't want LibFabric to be another layer in your middleware. If you're aware of which provider that you want to use, you can do direct configuration, and it will essentially just move the provider calls and have you to be linked directly to your software stack implementation. This really minimizes the pathway to give you that portability without sacrifice on performance. The memory model is also a really hot topic when it comes to RMA communication, and what's the best semantic match for SHMEM is to have a full exposure virtual address space and not have to worry about pinning memory pages as you're trying to communicate, because this adds a lot of extra software in the communication path. So this semantic is also available with the LibFabric framework. Additionally, SHMEM requires a very rich atomic set from its network interface, and we made sure that this was something that was in LibFabric and even at a fine granularity. So now for portability, even though with LibFabric and the OFI working group, we want to move forward the networks of tomorrow, we still want to work on the systems we have today. And so for the SHMEM community, Cray is one of the main providers that the users today have that they have at their disposal. So currently we have supported or in the works of supporting 4 different providers through LibFabric. And just to mention, Portals 4 also can run over IB, and also there's BXI hardware in the works. So we can do sockets, which of course, as Paul was saying, is your most portable. You can run it on whatever system that you have at your disposal. There's also OmniPath generation compliance and the portability scope. And Cray is the one that we're collaborating a lot with other folks to get this provider up and running. BGQ is something that was also proposed to enable. This is more so just to try to take the scalability tests to the next level. So now I want to go through some of the areas that we found needed a little bit more work to provide that to accelerate some of our portability efforts and provide a stepping stone for some providers. So our initial memory model, which is still the memory model that we have today in the SHMEM-LibFabric code base, is MR scalable. And what's wonderful about this model is it's user-defined keys and that full virtual address space, which is a very nice semantic match to SHMEM. And the other thing to note with this is it's a very minimal footprint. You're no longer exchanging keys, no longer tracking offsets or memory region pinnings. Furthermore, there was also an assumption about the OS support could support symmetric addressing. When we mapped the symmetric heap, we assumed that it was going to be symmetric across processing elements. Again, great match for SHMEM, and a very minimal footprint. You don't have to track the offset per processing element when you're trying to communicate. However, it's not the most portable at this time. And so, like I said, to create a stepping stone for some providers, we found that MR Basic was a good way to get this SHMEM-LibFabric working with other providers, as the utility aspect of LibFabric is still under development. And so with MR Basic, essentially what we're doing, the semantic difference is now a fabric can have defined keys, and so it lifts the user-defined key requirement. Additionally, for portability, we don't want to always assume that the operating system can support the symmetric addressing capability. And in this way, we enabled the remote offset capability so that you can track the offset for your processing elements. And so this is really the matrix of what is now supported in terms of the memory model today. Additionally, the atomics model was a little bit cumbersome as well. We want full atomic support, and we still do want that for SHMEM. But and across providers, certain providers are either full software atomics or kind of a sprinkling of different enabling in terms of the atomic capability matrix. But the one that kind of rang true across providers was long double atomic support. And so, in our Git info discovery in SHMEM-LibFabric, where we're trying to figure out which fabric is compatible with the requirements we are asking for, we didn't want to stop a fabric just because it had one hiccup or one area that it couldn't support. Additionally, we found that this particular spot in SHMEM shows up in a collective, the reduction collective, which is heavily used by the SHMEM community, and we thought it could be the performance in terms of a software enabling of this atomic was best suited in a new collective algorithm implementation with software atomics. And so now essentially what we've enabled is we lifted that initial Git info restriction so that later in the FI atomic valid detection, we can, at a very fine grain granularity, we're able to detect exactly which limitation there is in the fabric, and if it's long double, then we automatically hook into our recursive doubling software atomic implementation of the reduction collective. So today I'm just showing you a snapshot of the work we've been doing. This work absolutely is continuing to evolve, and this is just where we're at today. So currently for scalability, we had a PSM2 system at our disposal, and we were able to scale to 2,048 processing elements using the integer sort benchmark, which is a NAS parallel benchmark implemented for SHMEM, or it's an instance where it's implemented for SHMEM, and this is open sourced. Furthermore, we also tried scaling sockets, and we ended up getting enough time to run up to 512, and we ran the OSU SHMEM test suite for this. For performance, as I was saying earlier in the talk, a thin transport implementation layer is going to be really indicative of a tight semantic match between the application and the network interface, and this shows in our instruction counts, where we have a very minimal instruction count set to get from a SHMEM RMA write, essentially, to the fabric interface through libfabric below. So in summary, it's really at the heart of the community to have collaboration between vendors and labs and users, and try to make a network interface that works for everyone for scalability and performance, but also as an open source community for portability. And so we've seen that for Sandia-SHMEM-LIBFABRIC that we're able to scale it already, and we have a very minimal instruction count and therefore a tight semantic match between the SHMEM requirements and what libfabric can provide. Additionally, we're working hard on the portability aspect as well. There are 4 different providers that we're either currently supporting or are in the works to support. And like I said, this is another collaboration front where we're working with some folks from the lab and also from Cray to get the Cray provider up and running. And we did make some shifts just to accelerate some of the portability work in terms of the memory model and the atomic support. And I just want to thank everyone for being here towards the end of the conference. And also, this has absolutely been a collaboration effort, which has been really great. Ryan Grant has been really helpful, members from various labs. It's great to get the feedback. And special thanks to Santor Sir and Jim Dinan for all their work as well. So thank you. That's it. Any questions?
So regarding the instruction count, did you include the counts in libfabric, or is it just inside OpenSHMEM?
It's inside OpenSHMEM to get to the libfabric interface.
All right.
Yeah.
Thanks.
Any other questions? Okay.